Before we start, I just want to let you know, I have a website with resources for Chemistry Olympia. This is the link. So you can get, my personal information from the website, as well as a lot of, good resources, mainly made by myself. There are a few, summary, made by other students and teachers. I think they are really helpful for you to prepare no matter the local exam, the national exam, or even a higher level like study camp or even the team selection. So if you are interested, please take some time to go over my website. I'm also offering a national prep class right now. We just had the first session 2 days ago. Here is the syllabus and the plan. As you can see, we're mainly focused on the challenging topic in the USNCO National. The first one, I think you agree with me, probably very challenging for most of you, is descriptive chemistry and the laboratory. So we spend 2 sessions on this topic. The second part is organic chemistry, right? Organic chemistry is well known to be, challenging. So I plan to put 3 sessions to explain organic chemistry. And as you can see, I purposely put these 3 sessions in 3 different weekends, because in this way, you guys can get a little bit more time, to do more self-study. And otherwise, if we kind of, put everything together in a whole weekend, that might be too much. And some other time will be put in explaining and extending, summarizing some advanced topics, such as kinetics, equilibrium, electrochemistry. So the last session will be mainly used to talk about the explanation question in the national part 2. This part is also relatively hard to prepare, but in general, I will say it is assessing the relationship between structures and properties. So we try to summarize, the relationship. Hopefully it can give you a better understanding, make you more prepared and confident to work on this part. As you may all know, the ranking in the national exam is a little bit unique, right? So if you want to advance into the top 150, it's only related to your part 1 for most of the past year. So this is why we'll spend most of the class time to talk about part 1. But in order to support some more advanced students, we definitely will also put some time in part 2. Because actually, those topics are working for part 2 as well. For example, reactions and the laboratory, this part definitely will help you, get a higher score in the reaction writing part, right? Organic, the last question, right? Advanced structures is mainly for part 2. So here is the survey results based from a few students in my class right now about the topics they would like me to help them improve the most. As you can see, it's pretty much overlap with my plan, right? Mainly about reactions, descriptive, organic, equilibrium, electrochemistry, right? So I think I have a good understanding about the exam, have a good understanding about the students. So I believe the class should be helpful to support, my students. So just let you know, I have something like this. If you're interested, feel free, to get the information from my website and then contact me. So the class, you can sign up by April the 3rd, because after the 3rd, we will finish 3 sessions. That might be too late. Okay, no overdue. Today, we are going to talk about the National 2021 Part 1. This is indeed a pretty challenging exam. I need you to have 2 things ready before we start. The first one is the exam package. You need to access the exam package at any time, because I cannot show you all of the questions And maybe the contents on my screen is too small for you to see clearly, right? So you should have your own packet, no matter it's the printed version or you can access from your pad or your laptop. The second, you need to have a periodic table with you because we may need to access the periodic table all the time. So if you have this ready, I would like to run the discussion session today in this way. So first, we'll discuss the 5 topics which are not so related to calculations. That will be, you all know the 10 topics, right? I believe. The first one is stoichiometry. Stoichiometry. The second one is descriptive and lab. The third one is IMF and states of matter, right? The next one is thermal. The fifth one is kinetics. The next one is equilibrium. The next one is electrochem. The eighth one is atomic structure and periodicity. The ninth one is molecular structure and bonding. The last one is orgo and biochem. I believe you are all, well familiar with these 10 topics, right? So we will focus on the non-calculation based 5 topics first, including descriptive and laboratory. IMF and states, there might be some calculation involved. For example, vapor pressure, right? But in general, most of them are not really related to calculation and density of the solids as well. And then it would be the atomic and periodicity, molecular and bonding and orgo. We'll focus on these 5 topics first, and then we'll leave another 5 which are highly related to calculation in the end. I planned for a 90-minute session, but that is the maximum time we'll have. If you do not have many questions, we can definitely finish earlier. So this is kind of, based on your request, based on the questions you have. So I would like to, do it in a survey-based model. For example, we will first discuss the first 3 questions in the second topic. That would be question 7, question 8, and question 9. So that means it will be corresponding to option A, B, and C. So if you want me to explain question 7, you pick up A. If you want me to explain question 8, you pick up B and then C. So if you do not have any question in these 3 questions, you can choose D. D means you have no question. You don't want to discuss this. So I will pick up the question with the most student interest. Does this make sense to you guys? Okay, if you have no question, I will start the poll. So right now, we'll be working on 7 to 9. Ooh. Wait a second, guys. I got a small issue. My apology. A, B, E. C, D. Save. Okay. Yeah, once again, we are working on 7 to 9. Yeah, if you have no question, please pick up D, okay? I need a few more submission. So this is why I need you to have the packet, because I probably cannot show you all of the questions on the page, on my screen. 4 more submissions, guys. Okay, we'll end here. So share the results with you. So we'll quickly talk about question number 7 and number 8, okay? Number 7, which glassware would be most appropriate for measuring 10.00 milliliter of distilled water? So pay attention to the precision. We have 2 decimals, right? That means we need to pick up a very precise volumetric glassware. This list includes 3 stuff. The first one, the burette. Burette is very precise. The second one is the volumetric flask. Sorry, volumetric pipette. The third one is the graduated pipette. What is the difference between volumetric pipette and graduated pipette? Graduated pipette is just like the graduate cylinder. You have multiple marks which can measure the volume, any volume you need, right? Unless it exceeds the maximum volume. But volumetric pipette is just like the volumetric flask. There is only 1 mark. So that means you can only measure the volume at this certain volume. You cannot measure at any other volume. So those 3 glassware are called precise volumetric glassware. So they can measure to the 2nd decimal. And you are required to read to the 2nd decimal, although the last digit, as you may know, is estimated, right? That is part of your significant figures, which means the graduate cylinder is not a choice here because this one is less precise. It can only read to the 1st decimal. And test tubes, beakers, regular Erlenmeyer flasks cannot be used for a serious volume measurement because their marks are not very close. And also the surface area of the liquid is very large. That means if you read a little bit off, the volume actually is off a lot. So I think we made it clear, right? For question number 7. Oh, by the way, I have a very good summary about this part, which is posted in my website. So if you're interested, feel free to get this packet. Actually, this is the packet I was used in my first session for the national prep. So you can get a little bit more details about what I just summarized from this packet about the volumetric glassware. Okay, find it from my website. If you cannot find it, ask me questions. I will, share the link with you. Okay, question number 8 is a little bit tricky, right? It's pretty straightforward for you to figure out. We may have silver chloride as a white precipitate. We may have lead chloride as a white precipitate. And lead chloride is well known to be soluble in hot water. So it seems like we should pick up A, right? Only silver plus is present because it is said the white precipitate forms which does not appear to dissolve in hot water, right? But actually, from a more practical way, lead chloride, even there is some lead chloride, you may not be able to observe a very obvious change because it mixed with another precipitate. It's very hard for you to tell the precipitate actually decreases in amount or not. So this question is really interesting, right? So as I mentioned, you just cannot tell, especially when the amount of the lead chloride is not that much. Although here we know they have the same, moles, they are in the same solution, right? But still, if just part of the precipitate is gone, dissolve is very hard for you to tell. So this is why the answer to this question is C. Is C. Okay, guys, I will skip question number 9, as you know, only one of you requested. So guys, could you please give me some feedback that this mode work with you guys or not? You can either give me a thumbs up or, you know, thumbs down, or, you know, any way you can give me the feedback.
It works.
Okay, great. Thank you. Thank you. Thank you all. So next, we'll move forward to 10, 11, and 12. I will try my best to put these 3 questions here. So once again, Q10, Q11, Q12 is corresponding to A, B, C, respectively. So D means no question. No question. Okay. So let me have the poll relaunch. I really appreciate, you know, you guys can submit your question on time because that will be very helpful for me to really pick up the most important, the most challenging questions for you guys. Okay, it seems like we are done here. So we will pick up question 11 and 12 for a brief explanation. We will skip question number 10. By the way, if you have any question about number 10, I have a, you know, relative well-prepared annotation. So I will put it in the chat. This annotation is also on my website. So that means if you didn't get the chance to ask the question for a certain, you know, problem, you can always read my annotation after the class to get more detailed information. Okay, give me a second, guys. I realize there are a few typos in the draft annotation, but besides that, I think it's already in a good shape. Interesting. Okay, I got it. Yeah, guys, I just put it in the chat box. Please download it because when the meeting is ended, the link and the documents are gone. Okay, great. So we will talk about number 11 and number 12. Number 11 is quite interesting. You know, it has a new background. Probably not many of us are well known about this, right? We all know when we heat the blue crystal of copper sulfate pentahydrate, the blue crystal will change into pale green, close to white, but not really white. And then I think the best way for you to see questions like this in the national exam is to use the method of elimination. Some of the statements are just wrong, so you can easily eliminate. Some of them are correct, but they might not be related to the explanation, to the question. So some of them seems reasonable and correct, but it might not be the best explanation. So please pay attention to this, right? So I think it's not hard for us to eliminate C. Heating causes reduction of copper 2 to copper 1. I don't think we have a good reason for this. And also, if you may know, copper 1 in a solid typically is brick red, such as copper 1 oxide, right? This is the fillings test. We use the copper 2 plus reduced by the aldehyde, and we can get a brick red precipitate, which is copper 1 oxide. But guys, I need to remind you, what will be the color of copper 1 plus in the aqueous solution? Do you guys know this?
Blue.
I didn't quite get it. What did you say, Andre?
Would it be blue?
Blue. That is the copper 2 plus, right? Copper 2 plus is well known to be blue, but here is copper 1 plus.
Is it green?
It's green. I will say it is colorless. Does this make sense to you?
Oh yeah, that's right. Because
yes,
it's the full subshell.
It's D10, right? It is full filled d orbitals, so there is no DD transition, right? So please do not only remember or memorize, oh, zinc 2 plus is colorless because it's full filled D, right? Extend this to many other ions, right? So guys, the ions in the solid state may have different colors with the aqueous ions. This is pretty common, guys. Okay, so I think we can eliminate C. For D, heating causes reduction of sulfate to sulfite. I don't think we have good reason for this because heating typically is an oxidation if there is a reaction, right? Or a decomposition, which is a non-reduction. But it's very hard, for a heating process to be reduction without adding any, reductant, right? Here, we just heat it in the air. So there's no reductant added. So I think now we can narrow down to option A and B. Let's read it. A, heating causes water molecules bonded to copper to be replaced by sulfate, lowering the energy of the light absorbed. Option B, heating causes an expansion of the lattice, leading to a decrease in the coordination number of the copper and raising the energy of the light absorbed. Sounds both correct, right? At least reasonable. But if you read, carefully, I will say this part might not be very reasonable, right? Heating causes an expansion of the lattice. If the water is gone, I would say, it's not an expansion, right? It would be a contraction of the lattice. So I would say B option probably is the most confusing option. The correct answer here actually is A, because A is matching with the CFT, which is the crystal field theory. That means different ligands have different splitting energy. So if we say this is an octahedral structure, then we know the 5d orbital are split into two groups. The lower one is called T2G. The higher one is called EG. You can read a little bit more details about what are the 3d orbitals here, what are the two here. Due to the limit of time, I will not explain too much, just give you, a brief general idea. So now, if we have a different ligands, and then the delta, the splitting energy can be different. And the color of the ions actually is caused by the transition of electrons jumping from a lower energy level to a higher energy level. So if this energy gap is in the visible range, and then we will see the complementary color of the light absorbed due to this transition. Does this make sense? So if the ligands is changed, the delta O, because this is the octahedral, the delta O will be different. And then it will be absorbing a different color of light and then give you a different complementary color. So, but what we are not really sure is whether this process will lower the energy or it will make the energy higher, because I don't think we can easily remember all of the order of the, it's called the chemical spectral series. I forgot the exact name, right? There is a long list, right? But it's very hard for us to remember the full list. So this is something you probably are not sure in the test, but I think we have a good reason to pick up A from A, B, C, D. So this is my explanation here. If you're interested, you can get a little bit more detailed information from my annotation. And I think you do better learn the crystal field theory by yourself, because this is the trend of the most recent years of national. There are many questions about this, especially in the part 2. Number 12 is also a pretty interesting question. I like this question a lot. So we are asking which of the following could cause the measured concentration to be higher than the actual. So this is a very typical error analysis question, right? So read a little bit more detail. We have a colored salt solution, and we already pick up the wavelength we want to measure, which is lambda max. What is lambda max? We know in a spectrum, if this is the wavelength, the unit typically is nanometer, and the range is typically 400 to 700. This side is purple, this side is red. And then this is the absorbance, ABS. Typically, we will get a spectrum like this. That means this is the lambda max, the wavelength with the maximum absorption, right? So if the maximum wavelength is here, can you have a guess or make a prediction? What is the color of this species?
Red.
Right? Let's have a try. I think it's a good practice if you can draw the color wheel. To be honest, I don't know. I always need to draw the color wheel to get a good sense. The color wheel can be complicated, but we can use a simplified model. That would be like this. We cut this color wheel into 6 parts. We start from red, and then orange, and then yellow, and then green, and then blue, and then purple. This is the rainbow colors, right? But the interesting thing is the purple actually is neighboring with the red, although they are very far away from, the wavelengths, the perspective of the wavelengths, right? This is something interesting. This is called the color wheel. And now we need to make a reasonable estimation about the color absorbed. So this is kind of in the middle, right? So I will say the color absorbed is mainly green and yellow, because this is kind of in the middle, right? From red to purple, right? So that means the color of this species is probably in this range, either red or purple, right? Red and purple actually are relatively close. They are relatives, right? For example, like permanganate, it is purple. But if you dilute the solution to a certain degree, you will see the color is kind of pale pink, right? It's pale pink when it's very diluted. So that means purple and red are relatively close in the color. So this is a little bit extension, right? Just give you a sense. You can get the complementary color of the light absorbed. Back to this question. So now we use the maximum wavelength. So for error analysis, my suggestion is do not simply pick up A, even you think A is absolutely correct. I have 100% of confidence to say A is correct. Please still read B, C, D until you find a good reason to eliminate each of them because something you believe in actually might be wrong, right? You have a misunderstanding. Okay, let's read it one by one. The cuvette is now rinsed with the salt solution after being washed. That means there will be some water residue in the cuvette. That means if you add the salt solution is diluted with a small degree. If the solution is diluted based on the Beer's law, the absorption should be lower than its actual value, and then you will get a lower concentration. So A is not right because we want to find a overestimated case, right? Option B, the cuvette is not wiped off before it is inserted into the spectral photometer. If it's not wiped off, that means there might be some solution residue on the outer wall of the cuvette, right? Or there might be some fingerprint from your hands, right? So either of these two may cause a higher absorption because fingerprint can block the light, which will increase the absorption, right? And some solution residue on the outer wall will also increase. It's a kind of the light path now is increased, right? So absorption will be getting higher. So this one, I believe, will get your results higher. It seems like we are pretty confident now. Please still read C and D. Trust me, this is always a good practice. Less than the recommended volume of the salt solution is added to the cuvette. Less than the recommended volume. So if it's not too low, this will not affect anything. That means if the light can still pass through the solution, this will not affect anything. But if it's too low and the light cannot pass through the solution, you will get a zero absorption, right? So this one will be either no effect or lower. Okay, option D, the spectrum is set to a wavelength different from the lambda max. That means we pick up a different, wavelength. Obviously, the absorption is getting lower, right? But when you do the calibration curve, you are still using the absorption at the maximum wavelength. This will underestimate the concentration. Does this make sense to you guys? Okay. I'm not sure whether my explanation give you some new insight. Even in the beginning, you think you have no question. I hope this is the way, because I try to extend each question, not only finding the correct answer, but also extend as much as possible, right? But we are still limited by the time. Okay, great, guys. Next, I will jump to organic chemistry because descriptive and reactions and organic are the most challenging part in the national part 1. So this time, we will focus on 55, 56, 57. A, B, C, D is no question, okay? Let's still do the poll.
Dr. Chen, we can only choose one.
You choose, yeah, I think so. You may choose the most you want to discuss.
Sure.
Do you have more submission, guys? Okay. Great, thank you. So I think we need to explain question 56 and question 57, right? Okay, let's start from question 56. The question is asking about what is the best explanation for the higher reactivity of conjugated diene. First, we need to understand what is the diene. Diene means there are two double bonds, two carbon-carbon double bonds in the system. And the second question is, what is a conjugated diene? For dienes, we have three different categories. The first one is called separated diene. Maybe separate is not the best name, but the idea is there is no relationship between these two double bonds. They are kind of separated by an sp3 hybridized carbon in the middle, or more sp3 hybridized carbon. The second category is called conjugated, like this, which means the double bond is connected by a CC single bond. How to understand this is called conjugated? So we know all of the four carbons are sp2 hybridized. Do you guys agree with me? You need to add the hydrogens, okay? Because this is a line angle formula without showing you the hydrogens. And then you can apply the VSEPR model to get a good sense about the geometry of each carbon. And then you can further conclude, right, the hybridization. So which means if all of them are sp2, each carbon will have an unhybridized p orbital. And there is one single electron on each p orbital. So the case is like this. So we know this bond is a sigma bond. This bond is a sigma bond. This bond is also a sigma bond, right? So traditionally, we know sigma bonds are like head to head. The orbitals overlap in this way. Pi bonds are like this, shoulder by shoulder. So you will see these two are actually overlapping, although they are not in proportion. They look like very far away, but actually they have a partial overlap. And then these two also have a partial overlap. This is how we show the two pi bond here. But someone is not happy because they said, since we are also parallel and neighboring with each other, why now we overlap as well? The fact is they do overlap. So in order to explain, this partial overlap in between carbon 2 and carbon 3, so we have a model. We will say all of those 4p orbitals are parallel with each other. So the 4p electrons or pi electrons will be moving around in the system. So we call this process into delocalization. So this is the opposite word with localization. Localization means the electrons are limited in between the two atoms, just like the regular sigma and pi bonds, right? Delocalization, when do you hear these keywords, delocalization, in inorganic chemistry or non-organic chemistry?
With metals and the C electrons?
Exactly, the electron C model of metals, right? The delocalized electron C, we use this model to explain a lot of properties of metals, such as conductivity, such as malleable, right? So here we have the same idea. We'll say all of the 4 electrons are delocalized, and this process is called conjugation. We call this pi bond is conjugated with the second pi bond. So delocalization is corresponding to electrons. We say electrons are delocalized. But in terms of the pi bonds, we call pi bonds are conjugated. So this is a kind of, a molecular orbital way to interpret this. We can also use a more localized way, which is the resonance. we can draw two more resonances, although we know both of these two are not so good. They are minor, right? Because they have formal charge. And the formal charge are not so reasonable because you know the carbon anion, the carbocation are not so stable. But we know there is some overlap between the second carbon and the third carbon because this is already indicated by the double bond in the other two resonance structures. So in the conclusion, in the conjugated system, the single bonds in between these two double bonds should have some double bond character, which is confirmed by the bond length and also the rotation energy. Experiment told us the rotation energy of this single bond is much higher than a regular single bond, which means this bond is not freely rotation. So if we further extend it a bit, you will see these two structures are slightly different. This is called S-cis. S means the single bond. These two double bonds are on the same side of this single bond. We call it S-cis. This one is called S-trans. They are on the different side, right? Why we want to differentiate these two? Because S-cis can be used for the Diels-Alder reaction, which is the cycle addition reaction. If we react these two, we will get a six-membered ring. The Diels-Alder reaction is the most common way to synthesize a six-membered ring, a cyclohexane framework. But if you have this S-trans structure, there will be no reaction. You may have to rotate another double bond to the S-cis to have this reaction. Okay. If we talk back, we understand what is called conjugated dienes, right? The last category is called accumulated dienes. Something like this. You probably also know the structure because the central carbon has to be sp hybridized. The two terminal carbons are sp2 hybridized. So if we draw the two p orbitals, so one of the pi bond is on this plane, okay? It's in this plane, right? It's like this, they overlap in this way. But the right one between carbon 2 and carbon 3, they are actually overlapping this way. So these two pi bonds are perpendicular to each other. How do we know? It seems like pi bonds cannot be seen, right? We cannot really see the bonds, right? But we can see the hydrogens. Because if this is the way, the two hydrogens on this side will be like this, which means the two hydrogens are on the plane, which is perpendicular to my screen plane. But the hydrogen on this one will be on my screen plane. That means these four hydrogens are not on the same plane. This structure is called alene. If you're interested, you can further extend the chirality of the alene derivative. That means if we replace this hydrogen into a certain group, this structure will be chiral, which means it's not superimposable with its enantiomer. You guys can think about why it is chiral. Okay, back to the question. Now we got a good understanding about the three different categories of dienes, right? Separated, conjugated, and accumulated. Each of them have special properties. So now, compared to the non-conjugated alkenes, the regular alkenes, in electrophilic addition, we need to understand what is the electrophilic addition. This is the most common reaction for alkenes. We need to have some background about mechanism. Alkenes are electron-rich because the pi electrons are relatively easy to donate because they are loosely captured or loosely held or attracted by the nucleus. The pi bond is relatively weak, right? They overlap, partially, not like the sigma bond have to have. has a relatively large, stronger bonding. So this is why this electron-rich system want to attack an electron file. Electron file means it is electron deficient. File means philic, right? It likes electrons. So there will be an arrow to show the movement of the pi electrons to the electrophile, which means this is the nucleophile. And then if the E bonds to the right side, there will be a carbocation produced here, right? And then we can further have another external nucleophile to bind here. And we got a product like this. This reaction is called electrophilic addition of alkenes. So now we have a good understanding about the regular alkenes. But now if we have a conjugated alkene, follow the similar mechanism, this time we may got two different carbocation. If the E is added to the terminal side, the carbocation will be on the third carbon, 1, 2, 3, 4. But if the E is added on the third carbon, the carbocation will be on the fourth carbon. Guys, which carbocation is more stable? The top one or the bottom one?
The top one is more stable because the carbon is a secondary carbon and the one below is a primary carbon.
This is a very good point, but this is not the only or may not be the most important reason.
It's also an allelic carbocation, so it's resonance stabilized.
Great. Combining, these two opinions, this position is also allelic. What does allelic mean? There is a conjugation in between this double bond and this carbocation. Carbocation is also sp2, especially the carbocation on a saturated carbon. So if we draw the p orbitals, it will be like this. So the difference between our initial discussion is there is a single electron here, a single electron here, but there is no electron here. But we know these three p orbitals are parallel with each other, forming a delocalized system, which means the electrons from the left side will partially fill up in the empty p orbital on the carbocation, which will make the carbocation happy because carbocation is electron deficient, and now it is not that deficient anymore. So if the carbocation is happy, it is stable, right? So which means the first one is more stable than the second one. David also mentioned a good point because this one is also a secondary. This one is a primary, right? We know secondary is more stable than primary because more substitution means more electron donating. R groups, alkyl groups are generally electron donating groups, which will also make the carbocation happy. But here, this allelic, impact is very useful. It will stabilize the carbocation. So now I think you got a good sense. This will be the major carbocation, and then we will have the follow-up reaction. The nucleophile is coming and attack this part and get the addition products. So I think now you can easily understand why the conjugated diene has a higher reactivity compared to the regular alkenes, because it can form a more stable carbocation, which is allelic. Guys, I spend a little bit more time, to explain this because I really want you to have a good sense, because this is how we should learn organic chemistry, not only memorizing the patterns, the reactions, but understanding the relationship between structures and the reactivities. I think this is also the assessing point of the USNCO, especially in the national exam. They want you to not read the book, but really understand the reaction. So this is why compared to a lot of other countries' chemistry competition, they assess a lot of organic chemistry, but mainly about reactions or structure deduction. But the USNCO try to assess your understanding, explain the reactivity based on the structures. I think this is the key way to learn organic chemistry. So what is the answer here, guys? I think it's A, right? There's a concept called allylic. So talking about allylic, I think you need to know another keywords. If we have a carbocation like this one is also stable, pretty stable, because this carbocation is conjugated with even larger system, the benzene ring. So this is also a very special position. We call it benzylic, similar to the allylic, right? So I will not be surprised if this year in 2022 National Part 1, they assess you the benzylic position, right? But you need to understand, they are pretty much the same. Okay, this is question 56. 57 is, to be honest, this is really a relatively advanced reaction. If you read a college level organic textbook, you will see this reaction in the pretty later chapters, probably after chapter 15, right? So which compound will not form in the reaction of acetone, propanol with aqueous space? We know A will be formed. This is the hydration process. The reaction can be catalyzed by the base. What is the mechanism? We have the base to attack the positive charged carbon and open this double bond, because this CO double bond is already polar, which means this is your nucleophile. This is the electrophile. So what is the intermediate we got? We got this. Makes sense, right? And this one will try to gain a proton from the solution, let's say water. And then we got the target molecule, which is the 1,1 diol. The 1,1 diol. But 1,1 diol is relatively unstable. It's very easy to go back, to lose the water molecule back to the original ketone. So I would recommend you guys take some time after class to try to draw the mechanism of this dehydration process. Doing this way, you might get a better understanding about the mechanism here. You can also try if the reaction is catalyzed by acid, what will be the difference in the mechanism? So I will leave this part to you, okay? C and D are both related to aldol condensation or aldol reaction. The full name is called ALDOL. This reaction is pretty advanced. I will take some time to explain, but if this is the first time for you to hear about this, I would say this may take a while for you to understand. You may need to take some further time to fully understand this reaction. But I think it's worth for you to understand it because this reaction was assessed several times in the USNCO. So we have a acetone and we have base. You need to understand the alpha hydrogen. What is alpha hydrogen? Alpha hydrogen is the hydrogen on the alpha carbon. What is alpha carbon? Is the carbon directly connected to the functional group. For a ketone, the functional group, no doubt, is the carbonyl. And then this carbon are both alpha carbon. So there are 6 alpha hydrogens in total. So the alpha hydrogen has special reactivity. I will show you why. So if the base attack this alpha hydrogen, this bonding pair will transfer back to the CC bond and then further open the CO double bond. We will get
an enolate.
Yes, an intermediate like this. This one is called an enolate. Why it's called enolate? Because it is the conjugate base of a enol. What is the enol? It's ENE plus OL. ENE is the double bond, CC double bond. OL is the OH group. So enol conjugate base is called enolate. So the enolate has a resonance structure of carbanion. I would say probably this structure is easier for you to understand. So for the later discussion, I will use this. So now you see there is a carbanion. A carbanion is a good nucleophile, right? And now at the same system, we also have an electrophile, a positive carbon. Oh, guys, please be aware this reaction is reversible and actually favorable to the left side, to the reactant side, because this hydrogen is not that acidic. So only a very small portion of the ketone or the acetone will change into the enolate. So the majority of the acetone is still in the carbonyl form. So with the nucleophile and the electrophile in the system, we'll have this addition. This is the addition reaction, right? We call this process into nucleophilic addition, because the carbonyl is attacked by a nucleophile. So now, guys, I would like to leave you 20 seconds for you to draw the products, because it is very easy to make mistakes when you draw the products. If you are able to annotate on my screen, feel free to do so. We have a lot of empty space in the right side. We need to realize which bond is newly formed. Oh, this is very good. Thank you, Yue. So let me finish my drawing. You need to understand, this is the nucleophile. This is from the nucleophile. This one is from the electrophile, right? Carbons are here, carbons. So we got this. If this one is protonated, gaining a proton from the solution, we got the first step products, which is called a aldo. The reason why it's called aldo, Al here means an aldehyde. Sorry, not just Al. Ald here means an aldehyde. Ol means OH. So you already see the OH, right? But this part is a ketone. But ketone, aldehyde are both good, because if there is a hydrogen here in the beginning, you will have an aldehyde. So we just call this process into aldo reaction. But this reaction is not done yet, because this aldo is very easy to lose water molecules. How to lose the water molecules? There is an alpha hydrogen, right? Still on the alpha carbon. There is a OH. If we can lose a water from here and here, we will get an alkene like this. And this alkene is very special. What is the unique structure character of this alkene, guys? Something we just discussed.
It's delocalized.
Exactly.
Conjugated, yeah.
The CC double bond is delocalized or conjugated with the CO double bond. That means this one is more stable, because a larger delocalized system makes the molecule more stable. So the final products will be like this, because this dehydration process is relatively easy to go. But the mechanism can be complicated. I will just give you a keyword here. The full name of this mechanism is called E1CB. You probably know E1 and E2, but the CB here means conjugated base or conjugated base. But I do not have time to fully explain this mechanism to you. So if you are interested, take some time to do more reading. So that means we solve the problem. C is the final condensation product. D is the intermediate, the beta hydroxyl carbonyl compound. The reason why it's called beta hydroxyl is because this is our function group or the major function group. This is my alpha position. This is my beta position. So on the beta carbon, there is a hydroxyl group. This is called beta hydroxyl carbonyl. If you have a structure like this, it will be relatively easier to lose water molecules because it can form a conjugated structure. This is called alpha beta unsaturated carbonyl because the double bond, the CC double bond is in between your alpha carbon and beta carbon. Okay, guys, this is how we got ACD, so which means B cannot be formed. B is also a very unique structure because this one is called pinnacle. That means there is two OH groups on two neighboring carbons. In organic chemistry, we also call this into glycol. That means it is a 1,2 diol, which is different from our previous, hydrated ketone, which is a 1,1 diol, right? They are both diol, but this one is a 1,2 diol, right? If you have to go, feel free to do so. I appreciate your participation. I will try my best, to share the recording at my first, convenience. Okay. No worry. You guys will not be recorded in the session. Only the share screen is recorded. Okay. If you are interested, you can further do some reading about this reaction. This one is called pinnacle. There is a reaction called pinnacle rearrangement. But I believe this is a more advanced reaction. The mechanism is also pretty fancy because this is a rearrangement. There is a change in the skeleton. But under this situation, we have no mechanism to form this glycol because as you can see, we have to reduce the CO double bond from the acetone, right? But obviously, we just add a base. We didn't add, reductants. So even you are not sure about what is an aldol condensation, you should be able to make a good guess because B need to have a reductant. But obviously, in the system, we do not have a reductants. So actually, if we want to make this change, we need to add sodium. We need to add sodium as a reductants. Okay, guys, I think we are done with these 3 questions. Then let's have a look at the last 3. Probably it will also take a while. Let's say this is A, this is B, C, D is no question. Guys, we are working on another round of poll. So please share your opinion. Okay, I think we got most of your submission. So obviously we need to discuss 58 and 59, right? 58 is asking, which compound would have the lowest CO double bond stretching frequency in its IR spectrum. First, we need to have some background about the IR spectrum. IR is related to the vibration of the bonds. We can imagine the bonds are just like the spring. It is vibrating, right? So it has its own frequency, and this frequency is related to two factors. The first factor is how strong the bond is, which is the K factor. In the spring system, we call this into the, I forgot the name. What is the name of the K in a spring based on the Hooke's law?
Isn't it just like spring constant?
Maybe, yeah, it must be a constant because it is characteristic to the spring. And then it is also related to the mass of the heavy metal in the hand on the spring. So for a chemical bonds, this mass is related to the mass of the two atoms, which make the bonds, right? So the relationship is like this. We don't need to care too much about this equation, but we should have a sense. If the bond is stronger, it will have a higher frequency. If the mass is higher, it will have a lower frequency. We need to get a sense about this. But here is asking you which CO double bond has the lowest stretching. You guys understand stretching, right? Like this, stretching, the stretching frequency, which means we are asking which CO double bond is the weakest. But we know a CO double bond is polar, which means, you know, if the bond is less polar, there will be less ionic character and the bond will be weaker. So if we convert the question into another easy to understand sentence is which CO double bond is the least polar, because the least polar should have the weakest bond, which will result in a lowest CO double bond stretching frequency. So now this double bond is our reference because it's just a regular CO double bond without any other, you know, impact. But for B, C, and D, they are all carboxylic acid derivatives, CAD, which means they can all derive from the carboxylic acids, right? If we replace the OH in the carboxylic acids by using NH2, we got B, which is amide. If we replace the OH into an OR, we got C, which is an ester. If we replace the OH into a halides, we got D, which is acid chloride. I think it's good for us to know the names, and then we need to analyze the electronic effect. So those groups all have a heteroatom in the structure. The heteroatom has lone pairs, right? 1, 2, or even more lone pairs. This lone pair actually can be involved in the delocalization because all of those three atoms should be sp2 hybridized in order to form a delocalized system. Because if they do not form sp2, let's say they follow the VSEPR, each of them will be a trigonal pyramidal structure, which means the lone pair cannot overlap or cannot perfectly overlap with the CO double bond. And then delocalization is weaker, right? Let me take the nitrogen as an example. So if oxygen, carbon, and nitrogen are all sp2 hybridized, you will see a single electron here, a single electron here, and a lone pair here, right? So this structure shows you a localized model because we say, oh, these two make a pi bond. But actually, this lone pair is not happy because I also want to be involved, right? I can also overlap with you, right? Why not? You know, I'm left out. So these 3p orbitals will make a delocalized system. And we also have another way to interpret this, because we can draw a resonance structure. That means this lone pair is donating the electron back to the carbon and open the CO double bond. We got a structure like this, right? This gives us a sense, actually, this double bond, this single bond looks like a single bond, but actually it has some double bond character, right? So here is the thing. If they are delocalized, which means those 4 electrons are kind of, spread in the whole system, in the 3p orbital system, right? So obviously, this lone pair is an electron donating lone pair because it makes the CO double bond less electron deficient, right? If you follow this way, it should be clear. That means this CO double bond should have some character of CO single bond, which will make the bond weaker. So we can use this resonance strategy to get the answer. So which CO double bond has the most CO single bond character, right? The CO bond with the most single bond character will be the weakest, right? So now we can compare. So now you will see the difference between this one and this one is a N plus or a O plus, right? Which one is more stable, guys? Which resonance is more stable, the N plus or the O plus?
N plus.
The N plus is more stable because
it is less electronegative.
It's less electronegative, right? Carrying a positive charge is easier for a less electronegative atom. So I will say the first one is more stable. If this one is more stable, that means this one will contribute more to the real structure. This is the principle of resonances, right? Which means B should have more single bond character here, which means we can eliminate C, right? And we can also eliminate A, because A is just a regular CO double bond, right? So it has the least CO double bond character at this moment, at least, among A, B, C, right? And now let's talk about the last option. We'll have the stuff like this. But this time, different from our regular discussion, I will conclude this one has a relative low contribution because the lone pair on the chlorine actually is on the 3p orbital, but these two are both on 2p orbital. So which means we need to use a 3p, which is much larger and far away to overlap with a 2p orbital. This overlapping is very limited. So this double bond is relatively weak. It has a low contribution. So which means the CO single bond here contribute less. So D is not our answer. But actually, if we need to rank all of the 4 options, we will say D has the highest CO double bond stretching frequency because we only discussed the lone pair donating back to the CO double bond. We didn't consider another factor yet, which is the inductive effect. The inductive effect is through the sigma chain, just based on the electronactivity. So chlorine is relatively electronegative. So it will try to attract electrons from the carbon, make the carbon more positive. In another way, the back donation is pretty weak. So the overall results is the Cl here is an electron withdrawing group. I think this whole strategy also works for explaining the reactivities of the substituted benzene. This one, as you may know, this is a deactivated benzene. Deactivated means the chlorine is an electron withdrawing group. And benzene, if it has a high electron density on the pi system, it will be more reactive because the mechanism is quite similar to the electrophilic addition of alkene. At least the first step is the same, right? The first step is the same. So an electron donating group will make the benzene ring higher in electron density, more reactive towards electrophilic substitution. This time it's not an addition because the system wants to recover the aromatic system, right? And if you compare this one, the phenol, the OH group is an overall electron donating group because the lone pair on the oxygen can successfully overlap with the 6p electrons, right? The p orbitals on the benzene ring and donate the pi electrons. Although there is also the electron withdrawing group through the sigma chain because oxygen is indeed more electronegative than carbon, right? But the overall result is still electron donating, which will make the benzene ring more reactive. So do we have experimental evidence to support this? Yes, we do. We know if benzene wants to do the bromination, Br2, we must add a Lewis acid because Br2 itself is not a strong electrophile. With the help of the Lewis acid, we can form a stronger Lewis acid, Br+, right? And then the benzene ring will attack the Br+. But if we have phenol, when it reacts with Br2, we do not need to add a cat. No cat is needed. And it will easily react at room temperature. This one, we need to heat it. And we'll have 3 substitutions at the same time because this one actually is a white precipitate. This reaction is pretty fast. This is kind of not common in organic reactions because most organic reactions are slow, low yield, many byproducts, need catalyst, heating, reflux, right? Take a long time, but this reaction is pretty fast. It can be used to measure the content or the amount of the phenol quantitatively and also qualitatively. So you can see it because the OH activate the benzene ring, make the benzene ring much more reactive, much more reactive. I think this is question 58. We took a while, right? Do you guys have any further question about 58? Did I make it clear? Because I'm not really sure about your background in organic chemistry. So I try to make it easy to follow and make it more detailed. If no, we will continue to talk about question 59. This one is slightly easier, but it also a reaction or a question about reactivity, right? This time is not to explain the reactivity like question 56. This time is to compare the reactivity based on the different structures, right? Okay, so reacting with acid, I think this is a comparison between 2 alkenes with 2 alkynes. Our first conclusion is alkenes are generally more reactive than alkynes. We have different angles to explain this. One easy to understand angle is once the H+ is added, there will be a carbocation formed. We can compare which one can produce a more stable carbocation. So you will see a sp, if it's an alkene, we will produce a carbocation like this. That means this carbon is sp2 hybridized. But if you have an alkyne, do a similar reaction. This carbocation will be sp1 hybridized. As you may know, sp1 carbon is more electronegative than sp2. sp2 is more electronegative than sp3 because sp has a higher s orbital character. And s orbital is lower in energy compared to the same layer of p orbital because it's more penetrated. It's closer to the nucleus, right? So this is a very useful conclusion. I think you should take some notes and remember this. You'd better know how to interpret this in terms of electronegativity. And we know carbocation is electron deficient, right? Which means an sp hybridized carbocation will be less stable than an sp2. Because more electronegative means less stable, right? So now we can conclude alkenes are in general more reactive than alkynes because alkynes produce less stable intermediate, the carbocation. So we can eliminate C and D. And then in terms of A and B, I think you can see this double bond is more substituted compared to the second double bond, right? The second double bond is terminal double bond, and the double bond in option A is in the middle, right? So we know more substitution means more electron donating group, which will make the electron density on the double bond higher. High electron density means easier to have the electrophilic addition reacting with the H plus.
So more substituted is more easily react with H plus.
You're right. Does this make sense to you? Guys, can I further extend this question to you? If we need to choose the slowest one reacting with acid, what will be the answer? It must be in between C and D, right? Can you help me pick up which one has the slowest?
C.
D? What's your reason? How about we have a poll? My question is, which one, A, B, C, D, has the slowest rate reacting with aqueous acid? Okay. So obviously, as I mentioned, the answer should be in between C and D because alkenes are more reactive. They are faster. So it shouldn't be A or B, right? So in terms of C and D, I think we can follow a similar idea, right? Because C is less substituted compared to D. So I would say C is the slowest because the carbocation has the least substitution compared to D, right? Compared to D. But it's kind of not a very good question to pick up in between C and D. But if we have to choose an answer, I would say C is the slowest because it's a terminal alkyne. It has the least substitution. More substitution means more electron donating groups, which can stabilize the carbocation. Okay, guys, we spent about 90 minutes, almost 90 minutes, finishing the discussion of two topics, but the most challenging two topics. Limited by the time, we probably should end the session here today. I'm not sure whether for the remaining parts, do you guys have many questions or not? Let's say if you do have questions, I'm happy to host another session on a certain day. Probably not very close because you probably need to take some time to read the annotation. How about I try to get some ideas from you guys. If you expect another session to talk about the remaining questions, you chose A, okay? That means you like another session. Sorry. If you don't need, you choose B, C, D, up to you. So only A is the positive answer, okay? Okay, it seems like most of you are happy with another session. So let's schedule another session. I will update you guys later in both my website and also in my Discord server. Stay tuned, okay? Lastly, if you want to get more detailed information about my national prep class, you can find it from here, okay? We will, hold a next session tomorrow night and our third session on Sunday night. So averagely, we'll have 3 classes every week because we have only 3 weeks more, before the national exam. So this is the limitation, right? We got the results in early April, but the national exam is in late April. There is not much time we can do some further preparation. Any last minute question for me, guys, before we end the session today? Okay, great. Thank you. Thank you so much for your participation and your questions and your participation. Keep tuned. I will see you next time. Bye, guys.
Have a nice day.
You too.
See ya.
Yeah. Oh,